In this video lecture, we're going to focus on atmospheric moisture. Now, to begin atmospheric moisture, let's concentrate on the phases of water. There are three phases of water. There is water vapor, then there is water as a liquid, and then there's water as a solid. Now, the molecule of water, H2O, is essentially like this. You have one oxygen and two hydrogens. So Mickey Mouse. Two hydrogens, H and H, are attached to an oxygen, H2O. H2O, hydrogen and oxygen. So that's the water molecule. All right, so let's talk about each of these phases and what happens in between these phases. Because we're going to take the molecule and you'll see the changes that occur within this particular phase change. Water vapor, it's a gas. So you've got these water molecules that are speeding by. You know, you could reach out and grab a bunch of water molecules because there's water vapor everywhere. Sometimes, if it's dry, you have less water molecules. If it's very moist and saturated, you have a lot of water molecules in the air. So water vapor is a gas. Then you go to a liquid. The water molecules are definitely more dense. So you have a lot more of these water molecules hanging around and forming the state liquid. So liquid as water. Then the solid. The solid is very interesting. We'll get to that when we get through the discussion of the phase changes. When we go from water vapor to a liquid, then what we do is we lose the heat. We lose the heat. And when we lose the heat, when we release that heat, we cool down. Therefore, you're condensing, or there's condensation. Condensation occurs when you lose the heat. And then when you go from a liquid to a solid, then you are continuing that loss of heat, and you are going to freeze that water. When the water starts to chill and get towards the freezing point, then the water molecules begin to shift their position and form themselves into a hexagon type crystal, hexagon crystal. And so that's what the shape of snowflakes. If snowflakes have 6 sides, hexagons. And so what happens is water expands because what the water molecules are doing, they are reshaping themselves into a crystalline form. And that takes on 6 sides. So you have the expansion of water, which is trapping air, atmospheric air, and keeping this in a solid form. So we have, again, we're losing the heat this way. We go from water vapor, we're condensing, there's condensation, it turns it into a liquid, we continue to lose the heat, and we freeze into a solid where the molecules are reshaping themselves into a hexagon type crystal. Let's go the other way. We're going to add the heat now. When we add heat, we melt the solid. We melt the solid into a liquid. We keep adding more heat. We want to bring this liquid to a boil, and out comes steam. We are now evaporating. We are evaporating that liquid, and it is because it's heat. We're adding heat. We're heating it up. Now, as you see, there's a space here. Well, this is where sublimation fits. Sublimation. Sublimation occurs between solid and gas, if you will, and vice versa. Now, one particular object that if you fish a long distance away and you want to bring that fish back home, you use dry ice. Well, dry ice is a very good example in how sublimation works. Dry ice is a solid. It's a block. And you don't want to touch this with your hands because you actually burn your fingers. But it's a very cold solid of carbon dioxide. Carbon dioxide as a solid. Now, by the time you get home from your fishing event and you open up the newspaper block that had the dry ice in it, it's gone. That is sublimation. It goes from a solid to a vapor, and without leaving a liquid. So we go from a solid to a gas, and that is leaving no liquid. If we were going to leave a liquid, then we go this way. We'd melt, form a liquid, and then evaporation. But that dry ice is essentially going from a solid to a vapor, a gas. So that is the phases of water that we deal with when we talk about atmospheric moisture. Another thing about the sublimation is that if it's snowing outside, it snowed, and then it's very cold, let's say 20 degrees outside. The sun is shining, but it seems like over days the snow is decreasing in volume. Well, the reason why it's decreasing in volume is not melting because there's no liquid, but it's sublimating. That snow is going from a solid to a vapor, if you will, a vapor through the process of sublimation. So those are the phases of water that we will deal with. All right, the next point of this is the relationship relative humidity has with temperature. Now let's start with a parcel of air. A parcel of air at one temperature, to start out with, we increase that temperature. We raise that temperature. What will that parcel do? Let's pretend that this is a balloon, a Mylar balloon. We filled it up with air. We increase the temperature. What will happen to that balloon now that we've increased the temperature? Exactly. It will increase in size. It will expand. Now, if we take the same parcel, same balloon, and we decrease that temperature, drop that temperature of the parcel, that balloon, what happens to the balloon now? Right, it will decrease in size. So this is a dry parcel. This is what happens when you have a dry parcel. You start with one temperature, you increase the temperature, the parcel gets very large. It expands. You take this parcel, and then you decrease the temperature, and you get smaller. So it shrinks. You take this parcel, put it in the oven, it expands. Take this balloon, put it in the freezer, it gets smaller. An easy experiment to try on your own. Now, let's take the same parcels, and let's add moisture to them. So here we have a parcel, and we're going to put 50% moisture in there. Now, to show you that there is nothing, the volume of water does not change, I'm going to put 100 milliliters of water in there. Just for example, we're going to increase the temperature. We know that that parcel expands when we increase the temperature. What happens to the level of the water when we increase the temperature of this parcel? Well, the answer is the water level decreases. The volume does not change. The volume of water does not change. So now we began with 50% relative humidity. We're now at, let's say 25% relative humidity, just for example's sake. We start with another parcel of water, 100 milliliters of moisture. We start out with 50% relative humidity. We decrease the temperature. We know that if we decrease the temperature, that the parcel shrinks. When the parcel shrinks, what happens to the water level? It goes up. So the volume has not changed. The water level goes up. Now we have 75% relative humidity. So what is the relationship between these two variables, temperature and relative humidity? They are inversely related, or they're opposites. They are opposite. When temperature goes up, the amount of water goes down. If the temperature goes down, the amount of moisture increases. So during the day, the relative humidity comes down. During the night, the relative humidity goes up. And let's have a look at this in a graph form, if you will. Here is temperature, and here is relative humidity. The solid line is temperature. We start during the day. Now it is nighttime. early morning. Now we're getting towards day. There's the maximum temperature of the day. Now let's look at the relative humidity with this dashed line. We start with this. The relative humidity increases during the night and then decreases during the day. So we start, the relative humidity is down. It's low during the day, and this is night, day. So day, night, day. So they're opposites. This is how they function. Now the question is, which two variables can tell us when it's going to rain? And the answer is not relative humidity. It is actually dew point. Dew point can tell us when it will rain. And that's the next variable that we'll go through with atmospheric moisture. Dew point is the temperature at which condensation occurs. Dew point is the temperature at which condensation occurs. It's the point where the atmosphere becomes extremely saturated. For example, if you have, for the rules, dew point will always be equal to or less than temperature. Dew point is always, 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 always equal to or less than the air temperature. Okay, so if we have a glass of your favorite beverage, and you've got cubes of ice floating in this, it's a cool beverage. Here, the outside of this glass, it is warm. It is warm. Now I'm going to put this on a table so we can see what happens to this. So we have warm air. We have warm air. The glass, the beverage inside, is cold. It's extremely cold. And so what happens is the beverage is dropping that temperature of the air adjacent to the glass. So the air adjacent to the glass is cooling. And when it cools, there's water vapor in this air. So when it cools, that's when we get sweat forming alongside the glass, on the outside of the glass. Some people think that the glass is sweating. That is actually the water, the moisture is coming from the inside. It's not coming from the inside, especially if this was a paper cup. It's not coming from the inside. What's happening is the glass is cooling the air adjacent to the glass or to the cup and forcing condensation to occur. So when you cool something, you're going to force moisture out. And that's exactly what dew point is. Dew point is the temperature at which condensation occurs. So you drop the temperature of something, condensation occurs. Or the other way around. Anytime that you meet the dew point with the temperature, you're going to force the moisture out. All right, so let's look at some numbers here and talk about at points of saturation, or where condensation can occur. So we have temperature. T is temperature. Then dew point is TD. And then the dew point depression, which is the difference, the TDD is dew point depression, is the difference between temperature and dew point. So if we're looking at this as an equation, what we would do is temperature minus dew point equals the dew point depression, the difference between temperature and dew point. All right, so let's look at some numbers here. Looking at numbers. So let's start with 70 degrees Fahrenheit. 70 degrees Fahrenheit, it's relatively cool, warm. It's warmish. It's cool. It's comfortable. It's basically where the average, what we set our home's temperature at. And if I put this dew point at 68 degrees Fahrenheit, dew point is expressed as a temperature, then the dew point depression is 2 degrees Fahrenheit. 2 degrees Fahrenheit. Now, these two numbers are very close together. When these two numbers are close together, then it is a moist environment. It is a moist environment. Let's look at another example. We start again with 70 degrees Fahrenheit. We drop this dew point down to 50 degrees Fahrenheit. Now the dew point depression is 20. The dew point depression is now 20 degrees Fahrenheit. This is indicative of a dry atmosphere. The temperature is extremely higher than the dew point, or vice versa. The dew point is extremely low from the temperature. So we have a dry environment. A dry environment. So here it's very moist. We're very close to the actual air temperature. And then we have this example where it's 20 degrees Fahrenheit is the dew point depression. It's very dry. So which one of these two, A or B, will we have large amounts of evaporation? The answer is B. B will have large amounts of evaporation because it's already dry. So any moisture that is out there, if you have a cup of water, is going to evaporate very quickly in relation to having a dew point depression of only 2 degrees Fahrenheit. So the closer that you get, the closer that you get, this is the dew point, and here's the temperature. The closer that you get the dew point to the actual air temperature, you increase the moisture availability or the moisture level of the atmosphere. The further that you get away, it becomes more dry. So this is moist. The numbers are very close together, very moist, and then very dry. Now let's associate the temperature, dew point depression with cloud height. And then we get into the rain signature. Okay. Now we have T, which is temperature. We have TD, which is dew point, equals TDD. Now we put another variable in there, a constant, which is 225 feet, which equals cloud height. So we take the dew point depression and we multiply it by 225 feet, and that gives us cloud height. So let's do this. 70 degrees Fahrenheit is the temperature. It's always going to be the highest number out of all of these, except for the cloud height, of course. Then we put 68 degrees Fahrenheit. 68 degrees Fahrenheit. That equals a dew point depression of 2. Now we're going to multiply that by 225, and we get 450. So the cloud height here in this example is only 450 feet. 450 feet. That's the cloud base. 450 feet. Now we go to 70 degrees Fahrenheit is the temperature. The dew point is 50 this time. 50. Then we get 20. Multiply that by 225 feet. We get 4,500 feet. Is that right? I hope so. Yep, that's right. So we get a higher cloud height. Now, tell me, which one is it raining? Is it raining when the cloud height is 450 feet? Or is it raining when it's 4,500 feet? Well, the answer is, it is raining when the cloud height is closer to the surface. It is closer to the surface. Now here's a trick. Here's a trick one. All right, we have 70 as the temperature. The dew point is also 70. That is 0 dew point depression times 225 feet equals 0 feet. So, is it raining? Yes, it probably is raining. What's another possibility? Well, this possibility would be fog. This could be fog. If it's clear sky, but you have fog at the surface, then the dew point depression is 0. The cloud height is 0. fog is a cloud. So it could be raining. If it's raining, you'll know it's raining. But if it's clear and there's fog outside, then it's a cloud height of 0, and you have a dew point depression of 0. So it's very moist, extremely moist. So one rule to observe, and this is a general rule, is that cloud height of 1,500 feet and below will produce rain. You can have clouds that are with a base of 1,500 feet, 1,500 feet, and below can produce rain. Now, we'll go through the point where precipitation can occur. As I said before, relative humidity does not tell us when it's going to rain, and that's the common misconception. That you ask a student, tell us what variable tells us it's going to rain. Often you get relative humidity. Well, this is untrue. It tells us it already has rained. Dew point, on the other hand, tells us when it's going to rain. And this is how it works. So you have temperature. Temperature follows along, and then all of a sudden there's a slight increase and then a decrease. And then it levels out. Dew point, TD, it begins here, and then all of a sudden it starts to merge or rise with the temperature, towards the temperature, not with, towards the temperature, and then it meets here. Where you have this drop and rise, where the two lines merge, that is where we can get precipitation. This is what we call the rain signature. The rain signature. It is the point where the temperature drops and the dew point rises to meet, where they're very close together. And so the dew point is always going to be equal to or less than, at this point, than temperature. Always equal to or less than temperature. So the greater this merge, the greater the drop and rise, the more significant the rain becomes. The rain rate is increased. The more subtle that these two merge, it's going to be a lighter rain rate or a lighter precipitation, a drizzle, if you will. So this would be a cold front situation. This is what we would expect for a cold front passing and producing thunderstorms, a higher rain rate, a heavier precipitation. Here's what it looks like with a warm front. You have temperature, and then there's a slight decrease, and then a little bit of a rise there, and then dew point does the same thing. You're traveling along, and then all of a sudden you have a slight rise in dew point, and then it continues to merge. So you have rain signature there, and that indicates that there's going to be lighter precipitation. There's not much for it to go. So it's because it's already close together. I'd say it's probably 10, 11, 12 degrees dew point depression. And so this is a slight merge compared to the cold front, which was much larger. So again, this is the rain signature. This tells us when it's going to rain. And again, in order for it to rain, the values have to be very close together. You increase the probability of precipitation when you make these two numbers, the temperature and the dew point, move together, closer together, like 1 or 0 points from each other.